Hello and welcome to this Chem 651 Organic Chemistry video lecture. As promised, we are going to be talking about predict the product and synthesis problems that relate to the reactions of alkenes. We're going to start with some predict the product problems. So here we have an alkene. This is a methylene cyclopentane, called methylene cyclopentane because that's a CH2 group outside of the ring. Methylene cyclopentane has this exocyclic double bond. And we're going to react it with a variety of reagents. We'll start here with hydrogenation, which is all the way up at the top. If we hydrogenate, then we add hydrogen using a transition metal catalyst, and ultimately it results in the addition of 2 atoms of hydrogen across that pi bond. So we're basically just going to saturate this pi bond. Instead of being a pi bond, it'll just be a carbon now with a bond to hydrogen, and instead of a methylene out here, it will be a methyl. Or in other words, the product would look like that. Now it is true that the hydrogen adds in a syn fashion, so I could have shown the 2 hydrogen atoms adding syn, but it's also true that this carbon-carbon single bond that is formed upon hydrogenation is free to rotate, and so you lose track of where those hydrogens were added. And also there's now 3 hydrogens on this carbon, and you're going to lose track of which one you actually added anyway, so no need to try to show stereochemistry in a case like this. Here we're adding deuterium with palladium. This is basically the same reaction, except we're using the hydrogen isotope deuterium, and so we're going to get a very similar looking product, but this time we'll add a deuterium atom here and one of these hydrogens that would otherwise be a methyl group, where this is hydrogenation, is going to be a deuterium. So that's a CH2D group, and there's a methine carbon with 1 bond to deuterium. Very good. Let's move over here. We have mercuric acetate in the first step, followed by sodium borohydride in the second step. Those are oxymercuration reduction conditions, and we use them when we want to do a hydration without the possibility of a carbocation rearrangement. It will be a Markovnikov hydration. Now if we look at this alkene carefully, this is definitely an unsymmetrical alkene, so a Markovnikov hydration would mean that we add hydrogen across the less substituted carbon, that's this primary carbon here, and OH across the more highly substituted carbon, that's this tertiary carbon here. So that's what we're going to do. We're going to add hydrogen there and OH there. When we add hydrogen to this methylene group, it just becomes a methyl, much like we saw over here. And then of course we've added OH across the more highly substituted carbon. There is no stereochemistry here because this is not a stereogenic center. So no stereochemistry to worry about. No indication of rack. It's not a racemic mixture. That can only be true if this structure shown could be chiral. And when we write rack, it means you have a mixture, a 50-50 mixture of enantiomers. But this is achiral, so no need to write anything like that. Likewise, this is achiral. What about this one over here? We skipped over that. Is this achiral? It is. This carbon is attached to 2 hydrogens and 1 deuterium. 2 hydrogens makes it not a stereogenic center. This carbon is not a stereogenic center either. Okay, let's keep going here. We've got this alkene. Borane in the first step, H2O2OH minus in the second step. This is a hydroboration oxidation sequence. This is what we use to do an anti-Markovnikov hydration, which means we're going to get the opposite regiochemistry of what we just saw up here. With an anti-Markovnikov hydroboration oxidation sequence, we'll actually add hydrogen to the more substituted carbon and OH to the less. Notice that I didn't show that we added the hydrogen to the more substituted carbon, just as I don't show any of the other carbon-hydrogen bonds here or here. Let's look at this reaction all the way down here. We're going to take this same methylene cyclopentane and this time react it with HI. This is a hydrohalogenation reaction. We're going to add hydrogen across the less substituted and halogen, in this case iodine, across the more substituted, because this reaction we know is Markovnikov. We've added hydrogen across this carbon, now it converts it into a methyl group, and iodine across that carbon. Right next door, to the right, we've got a chlorination rather than an iodination, and we're using water as our solvent. Interesting. Maybe before we tackle that one, we ought to look at this one. This one is a bromination, but rather than using water or another polar solvent, we just use a standard organic solvent, which is methylene chloride. What we know about this halogenation reaction when it's run in an organic solvent, which isn't always indicated, is that it will lead to an anti-vicinal dihalide. In this case, that means an anti-vicinal dibromide. I'm showing it as though it has added anti, and indeed it would add anti, but again, remember that this carbon-carbon single bond right here is free to rotate. It would be just as appropriate to show this bromine sticking up. There's nothing you can do to stop it from rotating any which way it wants. Okay, now we're ready to tackle this one. Here is chlorination in the presence of H2O. Well, we're going to get a very similar looking product. We will add, however, instead of two chlorines across the pi bond, we'll add a chlorine and an OH. We call this halohydrin formation. Basically, if you think about the mechanism of the reaction, the chloronium ion that is formed is captured by water. The polar solvent is a weak nucleophile, and it will capture that chloronium ion. And we know that the water will go to the more highly substituted carbon. So ultimately, our OH will wind up at the more highly substituted carbon, and our Cl will be at the less substituted carbon. And once again, I'm showing this as though it's an anti-addition. It was initially anti, but there's nothing to prevent that carbon-carbon bond from rotating in this case. Over here, looks like I missed a hydration reaction. Here's my alkene, and there is H3O plus H2O. Those are classic conditions for an acid-catalyzed hydration. That's a Markovnikov process, so the product will look like this. I will add hydrogen across the less substituted carbon, which just converts it into a methyl group, and OH across the more highly substituted carbon. If that product looks familiar, it should, because we saw it once earlier. Way up here, we had our oxymercuration reduction sequence. It gave rise to the exact same product, and it should. They both give Markovnikov hydration products. The only difference is this reaction does not involve a carbocation, so there's no possibility for a carbocation rearrangement. There was no possibility for a carbocation rearrangement in this case anyway, because protonation led to a tertiary carbocation. If we tried to do a hydride shift from that cation, we would actually go in the wrong direction toward a secondary carbocation. We don't want to do that. So as we've discussed in class many times, just because there are carbocation rearrangements doesn't mean you're going to see one very often. It's only in select cases that you do. Well, it looks like we've covered all of the chemistry except for this one right here. Here we have bromine in the presence of an alcohol. This is a 2-carbon alcohol ethanol. It's very similar actually to this reaction here that we just did, chlorine in the presence of water. Instead of the polar solvent water, we're using the polar solvent ethanol. Look what happened here. In halohydrin formation, our OH wound up at the more highly substituted carbon. The same will happen here, but it won't be OH, it'll be OR, where R is this ethyl group right here. So the product of this particular reaction, there's the O-ethyl, which wound up at the more highly substituted carbon. And there's the bromine. And again, I've shown it as though it's an anti-addition, and it was initially, but because of this carbon-carbon single bond, you don't have to show it that way. That bond is free to rotate. Okay, so there's quite a few predict the product problems. Very helpful, I hope. Let's do some more predict the product problems Page 2. Here I have an alkene, and I'm going to treat this alkene with several reagents here at the top which form rings. MCPBA, that's the per acid that we use. It's one of the per acids that we can use to make an oxirane or an epoxide, and it doesn't really matter which one you call it, an oxirane or an epoxide, those words refer to the same thing. Notice that we're starting with an alkene which has some stereochemistry associated with it. This is the cis or Z2-butene. Not to be confused with trans-2-butene. We'll look at an example or two in a few minutes with that particular substrate. Well, we know that this epoxidation reaction using a per acid is concerted. And so if this alkene started with a cis stereochemistry, it's going to wind up with a cis stereochemistry. In other words, we're going to make a three-membered ring. Right across that pi bond, we're going to add an oxygen. That will be our oxirane. But because these methyl groups started out cis, and this is a concerted reaction where all the bond making and bond breaking takes place at the same time, then we're still going to have cis stereochemistry. So I have to put those two methyl groups cis with respect to one another. And likewise, over here I have diazomethane, which I'm going to use in the presence of light to create a carbene, the methylene carbene, which will cycloadd across this pi bond to produce a three-membered ring, which will be a cyclopropane. And once again, it's concerted, so since these methyl groups started out cis, they have to remain cis. Okay, very good. Let's come down here now. Look at this MCPBA reaction, and then in a second step, so first step MCPBA, second step H3O plus H2O. MCPBA is going to react with this alkene to form this very same structure I drew up here, this epoxide or oxirane. What's going to happen when I add H3O plus H2O? Well, those are hydrolysis conditions. We're going to hydrolyze the epoxide to a diol. So let's go ahead and draw that. We're going to have our two methyl groups adding in that fashion there. Let's see how I can best show this stereochemistry. Our two methyl groups have not added, I apologize. They were already present as a cis structure. So I think what I'm going to do here is use these two lines here to represent the two methyl groups, and then I've got the stereochemistry indicated at the remaining two carbons. And we know, as we've just discussed, that we're going to get an anti-diol when we treat a per acid with an alkene. Once again, we make an epoxide, and when it hydrolyzes, that gives us the anti-diol. So we're going to draw one of those OHs down, one of those OHs up, and the other two positions are just hydrogen, which you don't need to show, but I showed here in order to be clear about the stereochemistry. Anti-vicinal diol. Very good. What will happen here? First step MCPBA, second step, this is a methyl magnesium bromide. It's a Grignard reagent, so I'm going to pop that epoxide open with my methanol, with my methyl magnesium bromide. So if you think about this epoxide being attacked by this nucleophilic Grignard reagent, the two electrons associated with the carbon-magnesium bond would come in and ring open. If they came in from the back, there's the methyl. The OH would have to ring open to the front. And there would be the structure of my product. Notice that there is stereochemistry here. These are two methyl groups, so that's not a stereogenic center there, but this would be a stereogenic center here. Since I started this reaction sequence with something that is achiral and optically inactive, this must also be achiral and optically inactive, so I'm going to form a racemic mixture. Down here where I treated the alkene with MCPBA followed by an acid catalyzed hydrolysis, it looks like I also have a racemic mixture which must form in order that I'm not producing an optically active structure, which would be impossible starting with an optically inactive starting material. Back to this reaction again, MCPBA is going to give that product. Second step is the methyl magnesium bromide. There's the methyl group that came in from one side and popped open the OH group on the other side. And then finally H2O, that is just a quench. So we always use H2O as a quench step after we add an organometallic, and that's because water will destroy the organometallic if there's any left over. Really just part of the workup. But every time you use an organometallic in a reaction, you should expect that it's going to be followed by a water, sometimes H2O, H3O plus, some sort of an aqueous workup step. That's also the step where the O-, which was produced when the methyl magnesium bromide, and in particular the nucleophilic methide, came in and attacked and ring opened to produce an alkoxide, an O-. In this H2O step, you're going to protonate that. Again, you might see this as either H2O or H2O, H3O plus, but there'll always be some sort of a quench step that follows reaction with an organometallic. Okay, very good. Let's look at this reaction over here. This looks like an ozonolysis reaction. First step ozone, second step hydrogen peroxide, which is an oxidative workup. So we know that in the ozonolysis reaction, we're going to karate chop this alkene in half. There's symmetry here, so when you karate chop this one in half, the two pieces are exactly the same. So you're going to produce two species that look like this. See how I've just karate chopped that in half? And then the question is, what about this carbon-hydrogen bond, which would be right here? Is it going to remain? Well, not under these oxidative workup conditions. It will be oxidized to an OH group, leaving me with a carboxylic acid. So I'm going to create two equivalents of acetic acid. Contrast that with this ozonolysis reaction, followed by a reductive workup. Now this particular reductive workup is using zinc and water, but I want you to remember that you can also use hydrogen palladium or dimethyl sulfide. Those are three different workup conditions. You only need one of them. I just want you to be familiar with all three. Same reaction, we're going to karate chop that alkene in half, and we're going to produce two equivalents of a carbonyl compound, but this time, because it's a reductive workup, this carbon-hydrogen bond, which wasn't shown, will remain. And this is an aldehyde. So when you do a reductive workup in this reaction, you form an aldehyde, but when we did an oxidative workup, we formed a carboxylic acid, or sometimes just abbreviated acid. Okay, last couple reactions are down here at the bottom of the page. Now I'm starting with a different alkene. This is a trans, or E2-butene, and I'm going to treat it with MCPBA. I'm still going to form an epoxide, but because I started out with trans stereochemistry, I have to maintain that. If you look carefully, these are both stereogenic centers, which means I have to be producing a racemic mixture. All that means is that in addition to this, you'd be making its enantiomer, where this methyl group is in the back and that one is in the front. Why are they trans with respect to each other? Because they started out trans in this alkene, and this is a concerted reaction, all of the bond making and bond breaking steps occurring at the same time. Likewise, down here I have the cyclopropanation reaction conditions. Same thing is true. I'm going to make a cyclopropane, and I must maintain whatever stereochemistry was present in that alkene, so it's still trans. And once again, since this is chiral, I must be producing a racemic mixture, that plus its enantiomer. So that's quite a few more predict the product problems. Very good. Let's look at a couple synthesis problems. These synthesis problems I've taken from the book. They're scattered about the 5th edition of the book. Let's look at this alkene. It's a carbon-carbon double bond which is immediately adjacent to a quaternary carbon. If I did any kind of Markovnikov reaction, let's say protonate at the less substituted carbon to form a carbocation at this secondary carbon, a Wagner-Meerwein or methide transfer would be possible. A rearrangement reaction would be possible. And indeed, it looks like over here that's exactly what has happened. We've seen this reaction before. We've talked about this one in class a few times. This is going to be an easy synthesis. It's going to be just one step. All we have to do is add H3O plus H2O. If you go back in your notes from class, you'll see this reaction for sure. And if you don't have it in your notes for some reason, you can also see it in the book. This is a acid catalyzed hydration, protonate across the less substituted carbon to make a secondary carbocation. I would get a methide transfer to produce a tertiary carbocation. The methyl group has transferred over here. The tertiary carbocation was there, attacked by water, and after you lose a proton, you make this alcohol. So that's a pretty easy synthesis as syntheses go, one-stepper. And actually the next one's also a one-stepper. Look here. Look at this alcohol. It looks like a Markovnikov hydration, hydrogen across the less substituted, OH across the more substituted, but there's been no rearrangement. Well, we do know how to do this. These acid catalyzed hydration conditions won't work because they'll always give the rearranged product, this one, as the major product. So this is an okay synthesis because the major product is the product I'm showing as the desired product. This one right here would have actually been formed in this top reaction as a minor product, but now we want it as the major product. How can we do that? Well, this is going to use oxymercuration, reduction, sequence in order to achieve this Markovnikov hydration product without the rearrangement. And remember, the reason that there's no rearrangement here is it doesn't pass through a traditional carbocation. It passes through a very special bridged cation, a 3-center, 2-electron bonded cationic system. It's not a traditional carbocation, doesn't behave like a carbocation, and doesn't undergo carbocation rearrangements. Well, let's look down here. This one's a little bit different. Here, I'm trying to convert this alkene into this alcohol. It's actually a diol, not a simple alcohol, but a diol. Now I want you to notice that this tertiary butyl fragment on the molecule is still present in the product, which means there's been no rearrangement, no carbocation rearrangement. So we're going to have to choose some chemistry that does not involve carbocations here. This is where a little retrosynthetic analysis might help us. Look at these alcohols. These two alcohols are vicinal. Now they're drawn as though they're anti, but the truth is this carbon-carbon single bond is free to rotate, so it would be just as easy to swing this OH group around here, and now they would look syn in a different conformation. And for that reason, we're not really sure how they added initially. They could have added either anti or syn and still look like this. So let's think carefully about how it is that we can make a vicinal diol. We actually know two ways to do it. Both of them would start with an alkene, but they would move in different directions from there. So for example, if we had an epoxide, we could take the epoxide and hydrolyze it to this vicinal diol using either acidic hydrolysis conditions or basic aqueous hydrolysis conditions. Take your pick. You don't need to use both. You shouldn't use both. One or the other. That would get us there. But there is another way. The other way would be just to start directly from the alkene and to take the alkene and treat it with potassium permanganate in the presence of basic aqueous conditions, KMNO4OH-. That's going to convert that alkene into a syn diol, but again, because this carbon-carbon bond is free to rotate, that could easily have started as the syn diol, and I'm just showing it in a different conformation. In fact, we know another way to do that one. We don't have to use potassium permanganate. Another way of doing the same reaction to produce a syn diol would be first step osmium tetroxide, second step sodium sulfite, NaHSO3. So either of those, this is an either or situation, would do the job. Okay, so we look at where we're supposed to start. We are indeed supposed to start with this very same alkene that I've drawn down here. So I could in one step produce this syn-vicinal diol, or I could first go ahead and treat this with MCPBA, this alkene with MCPBA, to make the epoxide, and then create the anti-vicinal diol through hydrolysis. And once again, we're not sure if this started out as the syn or the anti-vicinal diol. This particular carbon right here is a stereogenic center. I must be producing this as a racemic mixture. Let's look at a few more synthesis problems. Here I've got this methylene cyclopentane, this exocyclic pi system once again, exocyclic double bond, and I'm going to try to turn it into a ketone. This looks like an ozonolysis reaction. And if you look carefully, if it were an ozonolysis reaction, I would chop that alkene in half, and one of the pieces that would be left would be this 5-membered ring. There would also be a 1-carbon fragment, which isn't shown over here as a desired compound, so it's presumably just going to be wasted. In order to convert this to that, I'm going to have to treat this with ozone in the first step. And then what about the second step? The second step, as it turns out, because I'm producing a ketone, there are no carbon-hydrogen bonds on either side of that carbonyl. It doesn't really matter whether you use an oxidative workup or a reductive workup. So I'm just going to write down that you could use either an oxidative workup, H2O2, or a reductive workup, like, for example, dimethyl sulfide. Either one would work in this case. Let's look at this one over here. This also looks like it might have been an ozonolysis reaction, and the reason I say that is because I'm producing a couple of carbonyl functional groups. So this is a ketone over here. On either side of the carbonyl is an organic carbon-containing functional group, a methyl group over here, and a methylene that's part of this whole fragment over here. But on this side of the molecule, it's clearly an aldehyde, a hydrogen on one side and a carbon on the other. So this looks like, since I produced an aldehyde here, that this was some sort of an ozonolysis reaction with a reductive workup. But the question is, what sort of alkene would have produced something like this? Well, think carefully about what the ozonolysis reaction does. The ozonolysis takes an alkene and karate chops it in half, and where there used to be a carbon-carbon double bond, there's now a couple of carbon-oxygen double bonds. So think carefully if these were carbon-carbon double bonds bound to each other. This is kind of a crazy drawing, I admit. Look at that long, crazy double bond. That's what that structure would have been like if we karate chopped that carbon-carbon double bond in half and then worked it up under reductive conditions to maintain the carbon-hydrogen bond here to produce this aldehyde. That would be it. In fact, that is it. First step, ozone. Second step, H2 palladium is one of my reductive workup conditions. But I can't draw this alkene this way. This is a crazy looking alkene. Let's look at it. It's 1, 2, 3, 4, 5 carbons. So it's actually a cyclic structure in which there is a carbon-carbon double bond. There's also a carbon-hydrogen there and a carbon-carbon leading to a methyl group right there. That's, oops, sorry, I was out of view. This is actually the structure right here, not that one, but this one. This is the structure we want to show. So in order, working retrosynthetically, in order to get that ketone on one side, aldehyde on the other, I would have had to take this cyclic structure, karate chop its carbon-carbon double bond in half using ozone. And then in the second step, do a reductive workup. I showed hydrogen. Palladium is my reductive workup. Okay, that's great, but it's not where I was supposed to start. If you look carefully, the alkene I had was this exocyclic alkene, and now I've got this endocyclic alkene. So let's come down here and figure out how to do this. This is actually going to use some older chemistry. Not terribly old. All of our chemistry is relatively new. But if we took this starting compound with this exocyclic double bond and we treated it with, let's say, HBr, we would do a Markovnikov hydrobromination, add hydrogen across the less substituted, bromine across the more substituted carbon. And then we could do an E2 elimination. There won't be any problems doing an E2 elimination in this case in very high yield, because we know that E2s do sometimes compete with SN2s, but look at that carbon that bears the leaving group, it's tertiary, so you're not going to have any problems with a competing SN2 reaction. I'm also using my E2 base of choice, which is a big bulky base. For all of these reasons, I'm going to produce a very high yield of the Zaitsev product, the more highly substituted alkene. It is true that you could also do an E2 elimination across here and produce the exocyclic alkene. That would take us right back from where we started, but that's not going to be the major product. The major product will be the Zaitsev alkene, that one right there. And then finally, that last step we were talking about, if we do an ozonolysis followed by a reductive workup, and the reductive workup conditions we chose were hydrogen, palladium, karate chop that alkene in half. This carbon-hydrogen bond will be retained, so I'm going to go ahead and draw that carbon-hydrogen bond right there. The rest of this will unfold. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is where there used to be a carbon-carbon double bond right between those two carbons, and so those become carbon-oxygen double bonds. So that was a little bit more challenging. Let's look at this next synthesis. I'm going to redraw it. This page has now gotten a little bit messy, so let's go ahead and redraw this over here. I'm asking the question, how can I start with that alkene and make this product right here as a racemic mixture? So there it is. That's the synthesis I'm trying to accomplish. Well, when you look at this, we have a three-membered ring, a cyclopropane. We only know one way to do that, so retrosynthetically this had to come from this alkene, which I then cyclopropanated right there using diazomethane, CH2N2, in the presence of light. That's the only way I can do that reaction. And we just worked through a procedure to go from this alkene to that alkene, so we're just going to reproduce it here. This time I'll use HI, but otherwise it is identical. We'll do the Markovnikov hydroiodination reaction and then follow it up with an E2 elimination. So it's a three-stepper. HI to produce the Markovnikov product, E2 elimination to produce the Zaitsev alkene, followed by cyclopropanation using diazomethane. Okay, last two synthesis problems. Take a careful look at these. We're starting with an alcohol now. Here's the alcohol. And we're going to try to make a diol. Look at that. That's an anti-vicinal diol. The OH group is coming out in front here. It's back behind the plane of the paper here. Those two OH groups are anti. So you got to be thinking, what reactions do I know that make an anti-vicinal diol? And then down here I want to make a syn-vicinal diol. These two OH groups here are syn with respect to each other. So I've got two syntheses here. One leads to an anti-vicinal-diol, one leads to a syn-vicinal-diol. Let's do one at a time. Let's do the anti-vicinal-diol first. What you need to notice here is that all the carbons in this starting compound map onto my product, my target. So I'm not introducing any new carbon atoms. All the carbons that were there at the beginning are still there. What I'm doing is I'm simply taking off this OH group and replacing it somehow, some way with a couple of OH groups. I must be losing a carbon-hydrogen bond here as well in order to get that OH on there. Clearly a lot going on here. We don't know one reaction to do this, and so this is certainly a case where we want to work retrosynthetically. We do know how to make an anti-vicinal-diol. We only know one way to do it. We would have had to start with something like this epoxide right here, which we then hydrolyzed. Hydrolysis of that epoxide with either OH minus H2O or H3O plus H2O would lead to the anti-vicinal-diol. Okay. And by the way, it may not have been indicated on here, but given that these two carbon atoms are both stereogenic centers, we would have had to produce this as a racemic mixture, and ditto down here. So the last step is secure. We must have started with an epoxide like this, treated it with OH minus H2O or H3O plus H2O hydrolysis conditions to produce this anti-vicinal-diol. The question is, how am I going to get from here to there? Well, if you think about this, you know that retrosynthetically there's really only one way we could have made this epoxide or oxirane. It would have had to start with that alkene. Notice the methyl group is right there. We're adding the epoxide across these two carbons, so that must be where the pi bond was. So we would have had to treat that with a per acid like MCPBA. So now the last two steps of the synthesis are known. From this alkene, we would have to go to that epoxide and then hydrolyze to give the anti-vicinal-diol. So it all boils down to how to convert this alcohol into that alkene. In order to do an elimination reaction, and we're clearly going to have to do an elimination reaction because we've got an alkene there, we're going to have to get rid of this poor leaving group and convert it into a much better leaving group. So let's just treat this with HI. This is that special SN2 reaction. First we'll protonate the OH to turn it into OH2 plus. Water is a good leaving group. Plus I minus, which will come and kick off the water and give me that iodide. I can then do an E2 elimination using my E2 base of choice, but because the leaving group is out here, my alpha carbon, there's only one of them, is right there, I would have to produce this exocyclic double bond, not the one I need to finish the synthesis. I'm going to have to then take that, this time let's treat it with HCl, do a Markovnikov hydrochlorination, followed by one final E2 elimination. And I'm going to spell this out for you now, all together from start to finish. Here we go. We started with this alcohol, which has a poor leaving group. We needed to convert it into a good leaving group, so I chose the reaction with HX, and in particular I chose HI. You could use HBr or HCl to put a better leaving group on board. Then I ran an E2 elimination to produce an alkene. It would have to be this exocyclic alkene because my leaving group is on this carbon right here. The alpha carbon is right there. That's the only alpha carbon. I'm going to pluck a hydrogen off that alpha carbon in this E2 elimination, actually pluck a proton off of that alpha carbon. And in this concerted E2 elimination, that places the pi bond right there. From there, I'd have to treat this with HX. I think I chose HCl initially, but I've switched it up now to HBr. Doesn't matter. That's a Markovnikov hydrohalogenation. Come back and do another E2 elimination. This time there's two possible products. This E2 elimination could take advantage of that alpha carbon and the protons on it and take me right back to this exocyclic double bond. But it could also take advantage of one of these two alpha protons to produce a more highly substituted endocyclic alkene. You'll make both products, but this will be the major product. The endocyclic alkene is more highly substituted. The Zaitsev product is this one. That'll be your major product. In a synthesis problem, we always focus on the major products. Well, I'm almost there. Now I need to treat this with MCPBA to produce an oxirane, which would look like this. And then finally, you remember we were trying to make the anti-vicinal diol, so I'm going to treat that with either aqueous basic conditions or aqueous acidic conditions. Do the hydrolysis reaction. And there it is. So it's a multi-step synthesis. Probably the longest synthesis we've done in this class so far. 1, 2, 3, 4, 5, 6 steps. I would say this is a pretty aggressive synthesis for us at this stage of the game. A 6-step synthesis is pretty tough, especially as all these reactions are relatively new to us. I gave you this one last because it really kind of talks about what we'll be doing in the future. Believe it or not, in Organic Chemistry 2, you'll feel comfortable doing 6 and 7 and 8 step syntheses, and you'll even do a few that are 12 and 13 steps, and they won't seem that hard to you. But right now, if this one seems really challenging, that's fine. It should seem really challenging. This was a pretty tough sequence. Well, that's the last of the problems I wanted to share with you. I will see you in class Monday. Good luck in your studying. Have a great rest of your weekend.